Hi there, this is Mike Masuda here at Evergreen Valley College at San Jose, California. I teach physics and astronomy here on campus, and I'm going to talk to you a little bit about atmospheric scattering. Now, typically when we talk about atmospheric scattering, we deal with just pictures and images on the whiteboard, but I wanted to also give this as a visual aid to show what is going on with our atmosphere. Now, this piece that you see here of glass, this is known as opalite. It's not opal, but it does kind of behave in a similar manner here. When light hits this piece of glass, the light going in tends to scatter off in different directions. And it turns out the shorter wavelengths of light tend to scatter off more compared to the longer wavelengths of light. And so violet light and blue and green, they tend to scatter off more compared to the red end of the spectrum. And so what this tends to do is it overall produces kind of like this baby blue sheen, as you see here, compared to the white paper that the opalite is sitting on. Now, this is kind of the analogy for the Earth's atmosphere. The Earth's atmosphere is made up of, molecules of oxygen, nitrogen, and atoms of argon, and a few other trace things. But when the sunlight has to pass through that atmosphere to get to us, some of the light gets scattered off into different directions, so it doesn't reach our eyes directly. But that scattered light tends to cause the overall sky to take on the colors that are being scattered, mainly violet, indigo, blue, and green. When you take those colors and add them together, it gives you this baby blue color that you see here. All right, and so this is not a bad analogy. It is similar to what we get for our atmosphere. All right, and so the opalite will serve as that analogy here, a model. So what I'm going to do with this, though, is I'm going to use a flashlight, this thing here. The flashlight actually is multicolor, and so I'm going to go ahead and make it a red flashlight here. And I'm going to take the opalite and place the flashlight on top of it like you see here and observe what is being transmitted directly through. And so what you see here is sort of like this blinky spot on the paper here. That is the transmitted red light. And you can see it's a fairly large amount coming through. The other stuff that is illuminating my fingers and elsewhere, that's stuff that's being scattered. All right, and so there is some scattering effect going on inside the opalite, as you see here. But for red, a lot of it is transmitted straight through. Now I'm going to switch it over to green, and that spot that you see on the paper there will be somewhat diminished. It'll be less. Okay, so we get a lot more scattering, which is why it appears that my fingers and the paper are much brighter, but the actual spot that the light is transmitting through the opalite, it seems to be a lot less. All right, so green light, which is a shorter wavelength compared to red, gets scattered more inside the opalite, and it's not transmitted as much directly through the opalite itself. We switch it to green, to blue, and we see that almost all of the light now for the blue light is scattered. Very little is transmitted through here, as you see. And so this gives us this idea that the shorter wavelengths of blue, they tend to get scattered in our atmosphere in a similar manner. Green gets scattered less, and then red gets scattered even less, okay, than green. And so we get this effect, all right, with our atmosphere, that blue tends to get scattered more. Now, what I'm going to do with this, let me go ahead and turn this off. Take the opalite and move over to another setup over here. So we have a setup with some batteries and a light bulb, and it's a very bright white light bulb that you see here. This is the analogy of our sun out there in space, unaffected by the Earth's atmosphere. The sun appears white in color out there in space. But beneath the atmosphere, the sun appears more yellow in color. Well, let me just demonstrate that. Putting the atmosphere in the way, look what happens to the light bulb color, right? Becomes more yellow. So the atmosphere does affect the color of the sun. A lot of the sunlight is being scattered off, and that's what tends to produce that bluish, baby blue color due to the fact that shorter wavelengths like violet, blue, and green are being scattered in the atmosphere, producing the baby blue color. Now, this is during the daytime. When the sun starts to set, the light has to travel through more of the atmosphere to get to our eyes because it's grazing through a greater amount of atmosphere. When it's directly overhead, the yellow sun is seen in the sky, but we can replicate this by making the amount of light passing through a thicker portion of the opalite. We get this effect here, right? So now, with a thicker, longer path for the light to pass through the atmosphere, the light gets more opportunities to scatter. And so what gets left behind is instead more of an orange color that you see here. And that's why the sky tends to become more orange, and the sun becomes more of an orange-red color during sunset. Now, to take this further, we take this whole thing now and flip it long ways this way and show you what it looks like this way. And we see that the sun is even more redder at this point, all right? But it is being transmitted through as this. Everything else gets scattered off in different directions, but we end up with some of the orange and some of the red passing through. And this is what happens during a lunar eclipse. So when the sun, earth, and moon are all in the same straight line, and the sunlight is trying to make its way to the moon during full moon, we end up with some of the light grazing through the Earth's atmosphere, all right? Traveling to us and then beyond us to go the other half of the atmosphere, going out of the atmosphere and finally making its way to the moon. And so the output from the sun as it travels through the filter of our atmosphere becomes this deep red color, as you see here. That light travels over to the moon to illuminate the full moon. Now, the Earth's shadow's in the way, blocking out the moon, but a little bit of the reddish light that is traveling from the sun through the Earth's atmosphere makes its way to the moon, illuminating it to become more of this brown-red color that you see during a lunar eclipse. And so that's why during a lunar eclipse we end up with that phenomena of blood moon, or when the moon turns sort of reddish in color. It's due to the fact that the moon is being illuminated by all the sunrises and all the sunsets on Earth at the same time. All right, I think that's it for now. Thanks. Again, this is the analogy, just an analogy. It is more complicated than this, but for the folks in conceptual physics and in astronomy, introduction to astronomy, this is not a bad analogy. All right, it seems to serve its purpose in being able to visualize what's going on. So if you want to get nitpicky about it and talk about Rayleigh scattering and other types of scattering, that's left up to the higher order physics courses. But for us, it's good enough to be able to visualize this stuff. All right, thank you.